Hi, and welcome to SMP's Tech Intelligence webinar series. This month, we are going to be discussing digital disruption in a network, and John Moorhead, our Senior Solutions Architect, will be walking us through his presentation. And with that, I will hand it over to you, John.
All right. Thanks. Thank you very much, and welcome, everybody. When it comes to disruption, people sometimes struggle with identifying what is disruption. What constitutes a true disruption? Is it just an overused buzzword in IT today? It may be, to the extent that some people even tune it out. But for those of you on the webinar, you may feel there may be a shift happening today. Gartner uses the term disruption as a fundamental shift. It is used to define a change with a long-lasting impact. The scale of digital disruption is increasing. They're happening more often, coming from many different places, cover large areas over time, and we are hearing a lot more about them. In fact, whenever people are talking about the future, and there are many predictions out there, the discussions typically focus around what is disrupting or may disrupt our lives. So, let's spend a few moments on the meaning of digital disruption. As briefly mentioned earlier, this disruption is a fundamental change or shift, which has a long-term effect in expectations and behaviors. And that change or shift can be in a culture, in a market, in an industry, or in a process that is caused by or expressed through digital capabilities, channels, or assets. Whereas a digital disruptor is any entity that affects digital disruption. So if we ask ourselves, what is being disrupted when it comes to networking? How and why are technologies like software-defined networking, SDN, and network virtualization, NV, causing a disruption? What are the drivers for this technology? What are the benefits? How are cloud services impacting networking? I hope to address and answer these questions as we go through the presentation. Gartner's list of emerging technologies is a good source to contemplate if there are indeed candidates for disruption, if they are not already. As we see, software-defined anything, SDX, is on this list, which includes but not limited to technologies like SDN and NV. Some disruptions are particularly noteworthy. One that we are at an inflection point about now is the second decade of cloud. And the first decade of cloud has been best described as a disruption itself. It caused a ripple effect in most, if not all, areas of IT. Implementation, software, development, outsourcing, networking, you name it. And as we move into the second decade, cloud is the modern baseline for pretty much everything that people are talking about as the next big thing. These next big things may be big data, the flip to digital business, machine learning, IoT, API economy, and even software-defined networking and network virtualization. Pretty much every one of these things requires cloud to an extent in order to fulfill a meaningful percentage of the potential they have to offer. Standardization, virtualization, and disaggregation are foundational elements of the wave of cloud architecture sweeping across the enterprise and service provider landscape. SDN has been one of the key drivers of innovation in networking within these architectures. And network virtualization is one of the main use cases enabled by SDN, which is growing and thriving. Networking in most clouds, public, hybrid, or private, achieve their connectivity magic through the use of network virtualization technologies. At the same time, SDN has also enabled improvements in the WAN, especially with the interest in SD-WAN by enterprises and the rollout of managed SD-WAN offerings by service providers. The open source scene in SDN has likewise matured, with continued momentum behind two leading SDN controllers, Open Daylight and ONUS, both hosted by the Linux Foundation. With Open Daylight as a platform foundation, we see the emergence of a second generation of SDN companies, Time will only tell if they will succeed where the previous generation did not. And as a network virtualization takes hold in enterprise and service providers, public cloud providers like Amazon, Microsoft Azure, and Google have built out improved network virtualization capabilities, making them an important part of the ecosystem. The drivers and benefits of both NV and SDN technologies are similar, which is not surprising since NV is often dependent on the use of an embedded SDN controller. The fundamental benefit of NV and SDN is that control of the network can be managed via software, usually a centralized manner. This allows network topologies, applications, security, and routing to be changed on the fly without having administrators log into multiple pieces of networking equipment and changing configurations to each one manually. It is well understood how virtualization can help a network scale. Fixed network topologies can be rigid and prone to management problems. New encapsulation techniques in today's overlay networks allow traditional VLANs to scale from 4,000 or so isolated networks to 16 million virtual networks by leveraging the most popular encapsulation protocol for data centers, VXLAN. Tied closely to flexibility, operational costs can be saved by reducing management overhead and time to launch a service or set up a network, including automation. The expansion of the commodity hardware market for SDN, as well as the demand for increased interoperability of networking gear, is reducing the number of proprietary networking products and pushing the networking industry toward greater standardization. Over time, this allows merchant silicon vendors to create high-quality, lower-cost products which contribute to lower hardware costs overall. NV platforms and their associated SDN controllers provide the capability to redirect traffic, apply dynamic traffic filters, and deliver quality of service QoS in most of today's implementations. NV platforms enable end-to-end visibility of the network and centralized management to improve overall performance. This can help identify problems and speed troubleshooting. Lastly, SDN controllers can enable network managers to control security of the network and applications from a central point. On the NV front, microsegmentation, the ability to apply fine-grained controls to traffic flows between VMs and containers, and to provide visibility into traffic flows, viewed as one of the key drivers to adoption of network virtualization technologies. Per a survey by SDX Central, when it comes to attributes that are important in an NV solution, there continues to be discrepancies between what end users are looking for and what technology vendor participants think are the most important attributes. Scalability and openness claim the top two spots amongst end user participants, whereas ease of implementation and openness for tech vendors. The SDN controller market continues to evolve with fewer commercial options for a pure SDN controller as compared to NV platform suites like Cisco's ACI and VMware's NSX. Different environments and installed equipment may require a wide range of support for southbound protocols, including but not limited to popular protocols such as OpenFlow, NetConf, OVSDB, and others. APIs are critical to SDN programmability. The richness of the API set will be a key benchmark. Organizations need to ensure that the applications have the API calls they need to be successful in implementing their particular use cases, which may include integration with operation and billing support systems, network management platforms, and more. Other requirements to consider are monitoring and visualization, performance and scalability, security and isolation, community support, application and developer ecosystem, and interoperability. The network virtualization market is still growing with a wide breadth of solutions and continuous innovation. When evaluating the context of NV solutions, we need to understand where most of them intend to deploy these solutions. Survey results of where they have or are planning to implement NV 60% of end users named the traditional data center and private cloud, and almost half noted they have or were going to deploy network virtualization technologies in their WAN and remote sites. This differs slightly from technology vendors, who are a little more eager to deploy it in hybrid cloud environments. Probably not surprising, telecommunications and service providers are the biggest adopters of SDN and NV technologies. No vendor is dominant in the network virtualization market as yet. Cisco Systems HCI solution and VMware's NSX are at the top with 25% and 23% respectively. In regard to vendors being considered versus chosen, Cisco, VMware, and Juniper are the ones to watch, with new age networks following closely. While many describe the abundant NV platforms as competitive in an apples-to-apples basis, the truth is that there are many subtleties to each vendor's solutions, including niche products and those targeted at specific applications. And certainly, clients who already have other products from vendors will be biased to selecting complementary products from the same vendors. For example, VMware ESXi customers picking NSX, Cisco Nexus switch customers picking ACI, etc. On the other hand, clients may opt to deploy NV solutions from multiple vendors. As another example, clients may choose both VMware and Cisco solutions since they may be viewed as complementary for client-specific use cases. So how do NV product strategies vary in the market? The products and positioning of all these NV vendors can, of course, be differentiated. One of the more fundamental aspects is the product architecture. There are really two main approaches to using network virtualization in data center deployments. First, direct programming the fabric is where the NV platform takes explicit control over the switches, creating and coordinating the virtual networks by directly programming the virtual switch and physical switches. This approach may require customers to upgrade the physical switches to support the appropriate protocols. A flow control protocol such as OpenFlow or a vendor's proprietary protocol will be used to manage the network. A majority of the latest manageable switches in the market today support some version of OpenFlow. Second, developing a network overlay may be accomplished a variety of ways. The most common is to modify or replace the virtual switch. In some cases, kernel modules are inserted into the hypervisor, most commonly with KVM. In situations where the virtual switch cannot be replaced and the hypervisor is proprietary like VMware ESXi, vendors may choose to use a VM running a virtual switch instance as the terminating point for virtual networks. In the overlay approach, multiple encapsulation protocols are available, ranging from straight GRE, IPsec, NVGRE, STT, and VXLAN, among others. Currently, VXLAN is dominant in the market with support with many physical switches and hardware-based layer 4 to 7 devices. Beyond purchasing network virtualization solutions from networking vendors or rolling your own using open source foundations, a portion of network virtualization purchases will be driven by network virtualization as a service, or NVAAS. NVAAS can be offered as a solution by a telco service provider as a managed on-demand virtual WAN offering, or by a cloud service providers as part of a public or hybrid cloud solution. Regardless, acceptance of NVAAS is on the rise. Cloud service providers who provide these network virtualization as a service solutions will often build their own proprietary solutions using their own technologies, sometimes open source, often not. For instance, Amazon, Microsoft, and Google all have proprietary NV solutions within their cloud offerings, none of which are based on any of the major commercial vendor solutions. Interestingly enough, they are also not based on the most popular open source platforms. As the adoption of SDN and network virtualization technologies grow, so do the deployment scenarios for SDN controllers. In the survey by SDX Central, they note that the respondents are primarily looking to use SDN controllers and NV technology to create virtual networks for cloud applications, including private, public, and hybrid environments. The next most popular use case is building out wide area networks for enterprises. Public cloud is solidly mainstream with most enterprises, and one look at the financial results at Amazon, Microsoft, Oracle, SAP shows how rapidly organizations, large and small, are adopting cloud services. However, the cloud era is still young as it evolves into a pillar of digital business. Indeed, most of the blue chip IT analysts and consulting firms continue to feature public cloud as one of the most significant technology trends. IDC predicts that by 2020, 2/3 of all enterprise IT infrastructure and software spending will go towards cloud-based technologies. Gartner identifies cloud and serverless computing, containers, and microservices, along with their associated APIs as the foundation of the next generation enterprise service architectures. Deloitte cites cloud services as one of the 5 long-term macro forces changing the role of IT within the enterprise. The combination of containers, which are widely used both on-prem and in the cloud, are transforming both enterprise IT and applications, with significant implications for networks. Fortunately, network virtualization and the increasingly programmability of network infrastructure, whether you want to call it SDN or merely programmable control and automation, have paved the way for cloud and container networks. Public cloud services run the gamut from low-level infrastructure to packaged applications. However, infrastructure as a service is the segment where the network implications are the greatest. The big 3 mega clouds each provide a similar set of compute, storage, and network services, which include the ability to create virtual private networks within cloud infrastructure and extending these back to private data center networks using either VPN tunnels over the internet or private circuits using a cross-connect service. Services from all 3 are similar and typically include VPC, VPN, firewall, NAT services, direct connect peering services, load balancing services, DNS services, both private and public, content delivery networks, etc. As we see, Azure networking services are very similar to AWS. Google Cloud Platform offers similar services as AWS and Azure. To conclude, network virtualization continues to evolve at a rapid clip, and the role of SDN controllers has changed in terms of their performance and go-to-market models. SDN controllers typically will not be sold as standalone platforms, but as part of overall network virtualization solutions. Public cloud services and container clusters will continue to change how application developers deploy new applications with ramifications on networks. Network virtualization will continue to evolve, with platforms growing to accommodate private, public cloud connections, as well as a mix of VM, container, and bare metal endpoint connections. There are predictions that SD-WAN will become the major use case for network virtualization, SDN, in the near future. If we plan accordingly and prepare for disruptions, we can minimize or eliminate the possibility of being disrupted ourselves. Being optimistic about change and digital disruptions can only help foster positive outcomes and assist with the possibility of realizing additional benefits that may be unknown to us at this time. I hope everyone found the information presented in this webinar helpful. Please contact SMP if we may be of any assistance with your digital journey. Thank you and have a wonderful day. I'll turn it over back to you, Jennifer.
Thanks, John, and thanks everybody who attended today's webinar. Keep your eye out for future webinars every last Wednesday of the month. as part of our SMP Tech Intelligence series. You can get information at smp-corp.com. Have a great day.